My name's Tim Paton. I serve as a technical advisor for Superior QC. We're going to talk about some of the benefits gained from high fidelity survey calculations and how those can help improve hydraulic fracturing positioning in unconventional laterals. This paper was written in collaboration with Bill Lesso. We presented at the ERTEC convention yesterday, actually. So basically, all directional and lateral wells utilize a standard method to calculate the well location from survey data. So minimum curvature, the most common method, assumes a constant rate of curvature between surveys. It's not true when drilling with mud motors. In some cases, the curvature changes are large and their location is systematic, leading to placement errors in excess of 50 feet. This is not insignificant in relation to the hydraulic fractures that are located with these sensors in effect. This is not a rare event in unconventional laterals and is not documented in standard survey reporting. This problem was addressed previously by Ed Stockhausen and Bill Lesso. I think that their paper was referenced earlier. So the motivating factor was the slide rotate effect and how minimum curvature approximation to the shape of your wellbore over a slide rotate interval can actually introduce errors into your wellbore survey. And this being the most impactful in TVD, but it can impact both TVD and lateral movement. So in reality, if you slide for 1/3 of a course length to get your expected dog leg and then rotate it out for the remaining 2/3, minimum curvature will connect those two surveys at the same angle change as a smooth arc. So it's basically assuming you're sliding the whole time, which is not true. What winds up happening is your MWD surveys are going to show you lower than what your actual TVD is. You're actually going to wind up higher based off of the order of your slide rotate method. So by minimum curvature being a poor approximation of the shape of your wellbore, this is injected error, and order matters. So if you rotate first and then slide, minimum curvature will wind up telling you you're higher than you actually are. And since you don't know exactly where you're going to survey in the slide rotate intervals, it could be a random walk. It could go up and down a few feet around 0 in terms of net impact, or it could accumulate on itself and cause a large TVD error and geosteering problems over the length of the lateral. So a traditional approach with survey management is a bolt-on approach. We said we can't model what's happening very well with the mathematical framework that we have, but what we'll do is inject a pseudo survey at the transition point from slide to rotate that has the same inclination and azimuth as the adjoining survey on the rotation segment. So we're saying the rotation segment is perfectly straight, and that gives a better representation of the shape of the wellbore, but feedback from the industry was, well, we get pushed around in the lateral while rotating, or we could have a rotary drop or rotary build tendency. So it wouldn't be correct to put all the angle change into the slide segment. That would make the dog legs look unreasonably large, which in some cases is a legitimate criticism. So what if we had a way to model what's actually happening dynamically in between those two static surveys? Then we could estimate rotary build weights. We could estimate rotary walk rates. We could estimate if your motor buildup rate tendency is not what you think it is going in the hole. We could estimate that error, give you better BHA tendency estimates, thus a better capture of the true wellbore position versus the error induced by minimum curvature from the slide rotate effect. And then with that, better BHA tendencies with which to project forward. Next slide. So today we're going to discuss the following subjects. We're going to talk about the directional sections of an unconventional lateral, the need for nudges in lease deployments, the tortuous nature of laterals, gun barrel and wine rack plots. So we'll give some examples. The cumulative effect of slides in relation to the MWD survey point, some examples of positional error from sensor accuracy and slide depths, tendency calculations and modeling high fidelity surveys, and the impact of the shape of a wellbore on a hydraulic fracture stage. And then we'll end it all up with some conclusions and then answer any questions that may arise. Next slide. So let's talk about the 4 sections that make up an unconventional wellbore. So we tend to break these wells up into a vertical section, a nudge, a build or a curve section, and a lateral. And for this presentation, we say a default lateral is 10,000 feet. We'll focus on the lateral section for most of this, as this section that's the section that's designed to intersect natural fractures or just to simply contact more of a productive formation. So with drilling, the concept's simple. We want to direct the bit in the direction you want to drill. As we all know, execution of that is not always as straightforward. So this is just a vertical section of a wellbore. Let's look at some plane views. So next slide, please. So this slide shows the nudges across 8 laterals on a lease. When we look at these nudges in terms of positional accuracy, so how well did we place our nudge is going to directly impact how well we drill our lateral and target as much pay zone as we can. So this in turn allows us to extract the most hydrocarbons possible across a lease. Survey corrections play a large role in this. Standard multi-station analysis has been in use for a number of years in the industry, and that approach has helped improve wellbore placement by estimating a handful of error sources and hopefully achieving a more refined result. Hi-Fi navigation is unique in that it's tied to a more advanced survey correction algorithm. Instead of looking at a handful, we're going to look at all error sources. And then through a fundamentally different mathematical approach, you're better able to estimate your BHA tendencies and thus more accurately place your wellbore. Next slide. So this is a snapshot of 50 wells. All of these wellbores have been snapped to an 8,000 foot landing point with 500 foot of displacement. So what we see are many different wellbore shapes. Some have a massive undulation in the lateral and some have a very smooth profile. What we can take away from this is that there's a number of systemic drilling problems as well as existent errors that can lead to your wellbore position being significantly impacted. You can note that some of these have up dip, others trend in the other direction with a down dip, and some of them, we're targeting a pretty flat plane. But what we see is that a lot of the errors, a lot of the undulations come from the systematic nature of conventional drilling. So what we have to do as an industry is address these errors. If we have a better way to model the wellbores, we'll be better prepared to respond to these shifts and get rid of these undulations in real time and thus drill better producing fields. So next slide. So let's take away some of that noise that we see. Let's just look at one wellbore. So the blue line here represents the planned path. You can see it's a smooth line. There's some changes in TVD, but for the most part, we're keeping a pretty direct path. The red line is the actual wellbore that was drilled. And you can see that while the actual wellbore, it captures the planned path, there are significant changes to TVD as the well is being drilled. So those undulations can lead to issues with completions, as well as increased time spent sliding to try to get back on that path. Next slide. So this is a gun barrel plot of the same well from the previous slide. So this plot is basically you standing at the heel of the well, looking out towards the toe. You can see the plan starts out to the left, comes back to the right, and then back left again towards TD. What the actual drilled path shows is that the well starts to the right and then comes back towards the left. A lot of this time spent sliding to get back to the plan can be avoided with the implementation of a more dense survey listing through high fidelity navigation. The ellipse you see here represents a default frac, so 800 by 600 foot frac. The variation you see from the plan versus actual is going to impact the center of the fracture. So if you expect the center to be exactly where you are in the plan, you're missing pay zone. Drift in this specific wellbore shows about 75 feet of departure from the plan. And then thus, real-time corrections can help you capture that movement and solve for that, those errors you see in real time. Next slide. So this is a combination of multiple gun barrel plots. With more wells drilled in an area, how is that specific field impacted? So this box represents a productive window plane, which for this specific acreage is about 57.5 acres. So the dark circles represent the heel and the light circles are the toe of the wellbore. When we analyze coverage for this field, we see about 57% of coverage for the entire acreage. Now you can see some cases where the wellbores overlap. In drilling, we talk about possible collisions in those areas based off of what your separation factor is. In fracturing, we could talk about those leading to frac hits. We calculated about 4% of overlap for this field, which means without that, it's possible we can move that overlap into actual field coverage, and then in turn extract more hydrocarbons. Next slide. So we've talked about placement. Let's shift and talk about the TVD error and where that's coming from. So while drilling, the DD is going to make their steering decisions based off of the bit, when to slide, when to rotate. The problem being the actual survey measurements are being taken at some sensor offset. For this example, we'll say 60 feet. And I know this will probably give some indigestion to the drilling engineers in the room, being 60 feet back from the bit. So as a common practice in the industry, you like to run as close as possible to the bit in order to help improve those decisions being made. But when you do that, you're injecting more error into the survey itself. So improper spacing below the sensor, getting as close to that bit as you can have a very significant impact on the accuracy of the surveys you're using to make those steering decisions. You compound that error by using it to model the position of your bit as well. Next slide. So when we talk about positional error, we say it's dependent on where the slide is made in relation to the survey sensor point. Normally what we see is a driller wants to get the slide done as close to the start of the stand as possible. That way it's out of the way, they can rotate out, and it allows the next survey to be taken after the slide is complete. So the driller can see the impact of the slide they just made. Systematic nature of drilling causes the error to expound as you drill the lateral. Looking again at this example, we can see that depending on where the slide is placed in the stand, it can lead to different results in TVD. There's a significant different curvature before the survey point than there is afterwards. If the slide straddled the survey point, we would balance curvature out and not have as much error. What this example shows is, again, with the survey point being 60 feet back, is that starting the slide at 20 feet into the stand would result in the least amount of positional error. Now, if the slide starts right at 0, we see that the wellbore comes in 9.2 feet shallower. If you start the slide at 10 feet, it's going to shallow the well even more, another 3.5 feet. And this is all over the course of 3,000 feet. If we shift the other way and start the slide at 30 feet, we wind up deeper. And this is all just based off of a function of where the slide is in relation to the survey point. Next slide. So this gun barrel plot shows the need for survey corrections. What we see in movement on this well is that the red lines, which represent the original surveys, have about 180 feet of placement error in them. With the corrected surveys in blue, which is your standard multi-station analysis surveys, as well as the high fidelity surveys in green, shows that by solving for the existing errors in the survey, we're able to get back to the center of the plan. Now, the survey corrections are separate from the hi-fi navigation piece. The multi-station analysis is solving for the errors in the surveys themselves, but they're not compensating for the curvature errors associated with those TVD shifts. Next slide. Now, this is the previous gun barrel we just looked at. What we see here is just the vertical section plot, and what we see is the multi-station analysis corrections actually lower the TVD, while the high fidelity correction actually raises the TVD. So this is a product of the multi-station analysis program not solving for those TVD errors. It shows two independent effects. And while both of these effects can be equally significant, you can't solve for both without a hi-fi navigation approach, which is, again, is going to solve for those non-constant curvature errors that you see. Next slide. So let's talk about some tendencies. What new information can we glean from utilizing hi-fi navigation? What we've learned is that these calculations are highly tool face dependent, but by utilizing this fundamentally new mathematical approach, we can show rotary build and drop rates, along with showing a more accurate motor yield or slide curve rate. What you can see from this slide is that the slide curve rate is an order of magnitude larger than the two rotary tendencies. Your build and drop rate in red and the rotary walk rate in green. What we also see is that the red inclination corresponds to build and drop, and the green azimuthal values correspond to the walk rate. So you can note the large walk rate corresponding to that survey azimuth out there around 18,000 feet. So the idea of this is when utilizing hi-fi navigation, we can better model the rotary tendencies, balance out the BHA, and reduce sliding. We have an example, it's not shown here, where we analyzed a 3-well pad brought to us by a geosteering department of an operator. Basically, they ran multi-station analysis in real time, and geosteering thought they nailed all 3 wells. They thought they were right in the middle of the zone. Now, the curious thing was when they took where they thought they were geosteering wise in relation to the top of the zone offset based off their gamma log, and added that offset to their geometrical TVD in the survey log, what they got was that middle well looked to be 30 foot lower than the two adjacent wells from the geometrical surveys. So when they plotted the geology from the top of their zone, there had to be this big valley in the middle of the left and right well. And geology was saying, no way, it's not geologically realistic that there's a 30-foot valley between the wells, but they're at the same TVD. And remember, multi-station analysis is not intended to fix TVD. But when we look at these wells with HiFi Nav, which is designed to identify and fix these things, HiFi Nav says, no, the middle well is 30 foot higher geometrically than you think it is. And so the geosteering team went back, they re-steered and plotted the tops of their zones with the TVD topographical map using the HiFi Nav solution. And that valley, that middle well supposedly drilled through, is gone. And all the wells are basically at the same level, which is what they thought they were seeing in real time, and which is what they actually had, but they were being confused by the geometrical error in their surveys as they were geosteering. And this is a great result and very impactful from a drilling standpoint. So the middle well had 20 target changes throughout the well because they couldn't figure out the formation dip. They couldn't figure out why there was such a discrepancy between their geometrical TVD and where they thought they were in the zone. So you can imagine if you're drilling with HiFi Nav in real time, you could probably cut those target changes in half or maybe 2/3. And then you start to think about, well, each time I have a target change, I'm having to slide. Now, how long do I have to slide for each time I make these target changes? And so if I can get rid of, say, 10 to 15 slides on a problematic well, what does that save me? And looking at that, you start to see a concrete financial impact. It's not coming up on production improvements. It's not about understanding your geology. It's drilling budget bottom line. Next slide. So this is an example of another gun barrel plot. What we can see with this slide is that, again, there's not a lot of survey error. So the original surveys are just about where the corrected surveys are, with the red surveys to the blue and the green. Again, this is looking heel to toe in the wellbore. What we can see on this, though, is that the HiFi surveys that are there in green, they show a significant departure on the TVD plane. Next slide. So in the vertical section plot, you can see there's about 80 foot of TVD error from the HiFi Nav result to the original surveys. So this was contributed to a slide rotate error in the lateral while drilling. What we saw in the analysis as well was a lot of structure in terms of change in inclination that was happening between the static surveys. It was not being captured by the standard MWD log. What we saw was the rotary segments had a significant build. Then the DD would slide hard to knock it back down. So rotate, build, slide, knock it back down, rotate, build, slide over and over again. So what we ended up with was a lot of inclination above the MWD inclination survey line that in this case accumulated into that almost 80 feet of error. So this goes back to accurately modeling the tendencies of the BHA. With the use of HiFi Nav, you're able to do that through a more dense survey listing, capturing what is actually happening between those static MWD surveys. Next slide. And so this doesn't only impact placement, this also impacts the curvature of the frac state. So this is an example of a 200-foot stage. The crosses represent the HiFi surveys. And as you can see, the density of these opposed to the standard 95-foot surveys from a standard MWD tool. Now, there's no way to show the completions team where the slide is in a section. The grayed out section of this shows what normal surveys would model through this stage. And with a HiFi, you can see the character of the slides and know where they are. And that helps to better define the shape of the wellbore and just help with the completions effort. Next slide. So in conclusion, I'd like to touch on the following. There are placement issues with slide rotate directional drilling that high fidelity survey modeling can address. It is different from traditional multi-station analysis work and sometimes acts in an opposite fashion. An intermediate result is the calculation of 3 directional tendencies: your slide curve rate, your rotary build and drop, and your walk rates. So these tendency calculations can be used to balance BHAs for smoother laterals, less sliding, and lower tortuosity. One thing that we have learned is that new metrics are needed to evaluate the placement of multiple laterals in a lease. The gun barrel and wine rack plots help to visualize that situation. So that's what I had. I'd like to open it up for questions.
I have a question.
Sure, Adrian.
Yep. So is this without the intention of oversimplifying, but if I were to use the live inclination and azimuth from an NWD and calculate, let's say, the position every 5 feet or whatever is the density I get, is this substantially different, or this will give me the similar results?
Yeah, great question, Adrian. So when we go back to that example where we showed the 80 feet of TVD discrepancy. So when we took that back to the operator and we said, hey, look, we're calculating 80 feet of discrepancy in what you reported and what Hi-Fi Nav is modeling. So they said, that's great. We had real-time ink. What does that look like in relation to the trajectory waypoints that were interjected with the high fidelity solution? So we took that, we overlaid it, and what we saw is that we had very good agreement with what the real-time ink was showing us. In some cases, Hi-Fi Nav was actually underestimating what was happening with that wellbore. So there were a lot of confirmations from the data that we did see. So it is good to utilize. The thing is that sometimes it's unreliable, right? So you know, how much can you trust it? How much you're going to utilize that in placing the wellbore as opposed to just a traditional minimum curvature approach, right? Just utilizing those static surveys. Mark, if you want to, yeah, can we go back up to slide 16? I don't have the example here. So this paper was presented at ERTEC. I didn't really want to commercialize it too much and put too much of some of the case studies. Mark, I can get with you after and actually show you where the driller was starting the slide in relation to where the MWD surveys were. What we saw most of the times is that he started the slide right at the top of the stand. He would slide it. They had about a 2-degree build. It would build up and then he would rotate. It had a rotary build, and then he would slide to knock it back down. So he was sliding in the middle. So he'd rotate out and then slide, rotate, slide. And that just accumulated on itself over the entire course of the lateral. So 1-run lateral, same BHA downhole the whole time. But yeah, Mark, I'd be more than happy to get with you and kind of show you some of that analysis.
Yeah, I can. Tim, can you see the? I'm unmuted. Can you see the chat that I have popped up? Robert Wiley had a couple on there Q&A.
Yeah, let me see.
It should be up on the screen if you're looking at it. I see Kevin McClure.
So yeah, I had one from Calvin.
Yeah, Tim, you had a slide that showed the 60 feet to the bit to MWD, and is there a rule of thumb or a preference? How I know I understand it's a BHA issue, but you pick your BHA. So
absolutely, yeah, Calvin, great, yeah, good question, yeah, for sure. So yeah, I think what you're asking is that, you know, is that what we're recommending? No, it's not necessarily. We're saying this is optimal for placement of the sensor. Obviously, we want to eliminate as much of that length between the MWD sensor and the tip of the bit, right? We want to get as close as we can. What we showed for this and what we modeled in order to kind of show an exaggerated effect of what would happen, and that's speaking specifically to the slide directly after where we showed where you start the slide in relation to the top of the stand will inject that TVD error. So no, 60 feet isn't kind of a rule of thumb. We're basically just talking about getting the slide started, how it's going to either build or drop the BHA, and then rotating out from there. So just dependent on where the slide is actually started in the stand will affect the TVD placement.
All right, there's Neil Bergstrom was asking about the assumptions on the slide in slide 11 showing the TVD error.
Yeah, Neil, I see that there. Bill might be able to answer that, how long the slides were that we used here, but this was one slide per stand. So this is one slide per stand, and then this chart shows a 3,000 foot accumulation of that error. So basically, what 30 stands is going to accumulate into this. I can't remember what the length of the slides were that we did on this, though.
Yeah, hi Tim, Bill here. So, I mean, this was a simulation to demonstrate the point, and the trouble with simulations is you got to get all the assumptions in there. So, I basically assumed that there was a constant drop rate of about 1 degree per 100 foot, and that when we slid, we would get 10 degrees per 100 foot. So we would introduce a very uniform slide to demonstrate the systematic nature of the Stockhausen effect, basically. And so and as Tim said, if you could straddle the slide so that half the slide was above the survey point and half was below the survey point, i.e. that green slide was around where that yellow dot is, then the error would cancel out and you'd get that green wavy line where you have a quick jolt of a 10 degree per 100 foot slide, and then the gradual drop of 1 degree per 100 foot. And what actually would be happening would be the green line. And then the end result from the stationary surveys, the 90-foot surveys, would be that straight line with, negligible change in TBD. But if you put your slide way above the survey point and basically violate the constant curvature assumption and minimum curvature, that's when you get these errors. And most directional drillers, as Tim said, they want to do the slide right away. They want to do the slide above the survey point so they can see the impact of the slide. And if they do that routinely, then we're going to get this effect that the well is going to be a lot shallower than it actually reports to be. It is very rare that a directional driller would do a slide deep in the sand towards the end of it and get the opposite error. So it's that systematic error. Of course, this was something that Ed Stockhouse and I identified 20 years ago now for offshore stuff. And when Ed and I saw 20-foot errors in 3,000-foot laterals, and then earlier this year when Tim reported to me that we had a lateral that had an 80 or 75-foot error, I got quite emotional. That was impossible, but when you think about it, arithmetic does work. We had 25 error in a 3,000-foot lateral. 3 times that would be 75 in a 10,000-foot lateral, and that's what we're seeing. So the systematic nature of directional drilling does hold here. So if you, this is a complicated slide, but I'm trying to demonstrate what happens. Of course, if the slide was all over the place, these errors would cancel out, but that's not the case. Did that answer? Did anybody else have any other questions about this? Because in the true directional drilling aspects of what's going on with it, this is the crux of the matter here. We're just surveying too far apart and violating constant curvature, and this is the result.
All right, thank you, Bill. I'll just stay on up if we have another.
Yeah, Travis has got a good comment there in the chat box. He said it'd be interesting to see how removing the sliding ops in the lateral with RSS, right? So rotary steerable. So we've looked at multiple rotary steerable runs. Travis, what we see is we kind of have the same tendencies that we see with traditional mud motors. A lot of it is dependent on that steer no steer, how they're downlinking to the rotary steerable and programming it. We've studied rotary steerable in multiple basins in multiple countries, and it tends to kind of go along with what we're seeing from the mud motors. You would think that a lot of this would be kind of taken out, but Now, it seems to be a constant thing that is indicative of rotary steerable and fixed bend motors.
So this is Chris Eli with Arrival Old Tools. So we manufacture MWD equipment as well, and through studies and through testing and through development and engineering, we've been able to determine the accuracy of inclination sensors under extreme conditions like high vibration issues and stuff is getting very, very accurate. So my question is that how is it not that you like the continuous inclination measurements by the foot in order to establish some type of continuous TVD curve in order to draw the conclusion of between points? So 95-foot stands, 95-foot sections. When we correlate the sensors, the inclination sensors in rotation, to the actual measurements at a static point, we're getting almost identical measurements. So why not just basically have two curves, have a standard curve that you're measuring at 95-foot sections, and then have an interpolated curve that you're measuring at foot by foot, and then compare those two? Why is that not different than what you're doing with mathematically between sections?
Yeah, so great. That's a good explanation of what your tool does. The way that we look at it is that we're bootstrapping the hi-fi navigation algorithm to our what we call fitter, right? So fault detection, isolation, recovery. So we talk about bolting it onto a survey correction platform, right? So when you talk about the error that's existent within your surveys, there's errors in there, right? Or else we wouldn't drill with ellipse of uncertainties. We'd be able to say that your wellbore is exactly where you think it is. It's on that imaginary line down hole, which in fact it's not, right? There's error existent within that. It's recognized by the OWSGs, the error models that we use when drilling, right? So we're assigning an ellipse that says our wellbore will be somewhere in here, right? So what we do with tacking it on to a survey correction algorithm and solving for all of the error sources simultaneously, instead of even just solving for a handful of them, we're taking out the placement error, right? So we talk about placement and then we talk about TVD, right? So it's kind of a two-part approach. You do kind of do the same thing when you're using your real-time inclination. Just from the studies that we've seen, the real-time inclination can vary. We can see, if you're tossing out those values that are bad, right, then you're doing well. But we just have seen that it's more accurate to eliminate the error that's existent within the actual MWD survey that's being decoded at surface, and then bootstrapping it with trajectory points we look at around between 13 to 15 foot. We'll be adding in a trajectory point survey and using minimum curvature to calculate there, right? So instead of just calculating over the length of that 95-foot course length, we're just doing it over a much smaller length now with a wellbore. Does that kind of answer your question?
I had something to that. Which one? This? Hey, Tim, it's Bill here. So, an add-on to Chris's question. I mean, your continuous surveys or let's talk an inclination. It's easier. Continuous inclination and stationary surveys at the same depth are going to agree. It's going to be the same survey. It's not really a problem of the actual measurement, though. As Tim says, we separate the survey accuracy, MSA or fitter part. The other one is environmental. It's the violation of constant curvature. Our solution from 20 years ago was to survey every 30 feet. 3 times, every joint instead of every stand. We reduced this particular environmental error by like 95%. So, and of course, the real problem was, don't confuse me with the facts. Nobody wants to have 2 sets of surveys, because while we say continuous ink and stationary ink are the same. They're not exactly the same. They're often hundredths. And then of course there's problems with azimuth, so you're going to get two positional calculations. And we battled this all through ISQA for, you know, from 2002 to about 2012. But some kind of recognition that we need some kind of survey update model every 30 feet or every 15 feet or something like that makes this problem go away. And the fact that we're seeing it, you know, that people are changing isopac in geological models because we have the Stockhausen effect, which is exactly what we're trying to address here, is amazing. So somehow let's allow, you know, let's in the directional drilling business allow for some method to check surveys more than every 90 feet, either with continuous and I long ago gave up trying to stop an actually stationary survey on every joint of pipe, and we don't have to. The measurements are accurate, even azimuth, even in the unconventional wells, cheaper MWD tools.
Yeah.
I mean, I had very good continuous azimuth in 2004, you know, for the deep, expensive offshore stuff. But, you know, we have that now.
Yeah, and Travis, just to go back to your question that you asked about the 6-axis data from the MWD measurement, yes, we do utilize that. We use the corrected 6-axis data that's generated from our survey correction solution. So we're going to take the decoded 6-axis data, correct that, and then utilize that in the HiFi nav calculations.